Today's class we are going to discuss about transmission line parameters and equations. So transmission line consists of two or more parallel lines. It is meant to transfer power from source to the load side. So it is a long transmission line, maybe it's a short transmission line, and it has many parameters, distribution parameters, series resistance, inductance, shunt capacitance, and shunt conductance. And for mainly two purposes we are using transmission line. One is to transfer the power. So for energy transfer is happening in two different ways. One is the power, the another is for the data. So if you consider a transmission line, this is source end, and this is the load side. So the energy is transmitting from the source to load in two different forms. So you can transfer the power. So the power is for energizing all your household appliances, or maybe the heavy equipments at the industrial sites or domestic sectors. And for data, that is means information, the transmitting information from one end to the other end. It may be for telephone or fiber optics transmission or radio transmissions. So anyway, we need the transmission network to transfer the power or information from one end to the other end of a transmission line. So let's see that more about what are the various parameters and how these parameters are connected to each other, and what are the equations we can derive out from these parameters. Let's see that. So these are the parameters. The one is R dash, it is effective series resistance. The transmission line is made of copper wires or aluminum wires. So these aluminum wires and copper wires possess some kind of resistivity. Due to the resistivity, it has some resistance. So we can connect resistance and resistivity using these expressions. So the resistivity depends on the type of materials. So all the transmission networks possess some resistance. So this resistance is also depends on the length of the transmission lines. So in all this derivation, today's derivation, we are connecting with our length in the direction of Z. So we will take Z as a direction. So it is the direction along which the transmission line network progress. So Z we consider as a length in this derivation. So the R depends on the length. Okay, if you are taking a very short transmission network of having length the delta Z, so delta representing a small quantity. So this is R per unit length, then the resistance can be write down as if it is R dash, then R dash. So it can be written down as R dash delta Z. So unit of delta Z is in meter, and R dash is ohm meter. So if you substitute here ohm per meter into meter, you will get answer ohm. Now let's see that this is the effective series inductance per unit length. It is a Henry per meter. Effective series inductance, because when the alternating current flow through the conductor, some of the counter EMF will produce which opposes the flow of current. So that form of that resistance can be expressed in the form of that is XL. So XL is the inductive reactance, that is 2 pi FL or omega L. Here it is L dash, so omega L dash. And this is also depends on the network length. So here L dash is the unit of L dash is Henry per meter, and if it is L dash delta Z, and the unit of delta Z is meter, so the total inductance is in Henry. So total resistance in ohm and total inductance in Henry. And the next parameter is G dash, which is the shunt conductance. Because in the transmission line we have the towers are there, the transmission towers are there, which is meant to support this the long transmission network, but it is not produce any kind of absolute insulation. So the current flowing through this transmission line, some of the current will flow through this the transmission tower, because this we can treat it as a leakage current. So this leakage current is because of the pure insulation coordinations and other conditions, just like the grounding of the transmission network, the transmission tower. So this parameter we can also incorporate it into our network model using G dash, so shunt conductance of line per unit length. So this D dash is also depends on the network length delta Z. If you are considering a small network of length delta Z, then the total shunt conductance can be written down as G dash delta Z. If you bring into that unit, that's Siemens per meter, that's the conductance unit, that is multiplied with delta Z is meter, so it is Siemens. And delta G is an inversely proportional to the resistance. G is inversely proportional to resistance. And similarly, the other parameter is the shunt capacitance. And here if you see that if the insulator is offering some insulation here, there is a kind of the parallel plate effect is happening here. See, this is a transmission network, it is carrying the current. Let us consider it as plus, and this plus will induce some negative in the surface, the ground, and these plus and minus are separated with an dielectric medium, so we can treat it as air. So because of the long transmission network, so there is some kind of capacitance will come into the picture. So this capacitance is because this transmission line we can consider as a positive charged plate, and the ground surface is we can consider as a negative charged plate, and in between the positive and negative there is a medium which is separated, that's an insulated medium air. So just coordinate this one with our the definition of the capacitors. The two parallel plate capacitors are separated by a small distance or a distance, some insulation medium, so which is an equivalent of capacitor. So this is we are taking into our model using C dash. So the total capacitance of the network is C dash into delta Z. C dash is farad per meter and delta Z is meter. So the total capacitance is F. Now we are taking all these four transmission line parameters into our network model, and let's see that how our network model looks like and how they are connected each other. Yes, here we can see that this is our network model, and this is our the source side and or input side, and this is our output side or load side. So the voltage is also a function of time, and it is also a function of the length. So we are considering voltage is a multi-parameter function of Z and T. Z is a line length and T is a time. So the one side of the transmission network is excited with V Z comma T. So V is a function of Z and T. So apparently what will happen? There is a flow of current from one end to the other end. The current also is expressed using Z and T. It is also a function of Z and T. And here the current I is represented as I as a function of Z and T. And we have seen that the series line resistance, so R dash delta Z. So this is the total line resistance because we are considering a line of having length delta Z. Now this is the total line inductance. This is the resistance of the transmission line, the total resistance of the transmission line, and this is the total inductance of the transmission line, inductance. And this one is the total conductance of the transmission line. So conductance and capacitance are always shunt elements, whereas the resistance and inductance are series elements. So this is the total conductance. The conductance because of the leakage current effect that is flowing through the insulation. So maybe some insulation damages, or maybe the weak insulation coordination of the disc insulators. Because of many other parameters, there is some current will flow from this point to this point. So that we are modeling using this conductance. So the total conductance seen by this network of having length delta Z is G dash delta Z. And similarly the capacitance of the network. This is the capacitance. C dash delta Z. So what is the current that is received at the output side? The current that received at the output side is changed by a small fraction because of the current is altogether, it is transferring from a length of delta Z. So it can be modeled as I as a function of Z plus delta Z and at time. Similarly, what would be the voltage at the output side? So this is also been subjected to a small changes due to the line, because we know that some kind of regulation will happen at the output side, voltage regulation. The voltage will gradually reduce. So if it is a heavily loaded, it is a gradually reduce. If it is a lightly loaded, its voltage will gradually increase. So that is a Ferranti effect. So that effect is also being taken into this our model using the function Z plus delta Z. And time is, which is an independent parameter, but the voltage and current all are time dependent. If you see this function of voltage, sinusoidal varying function, we can see that at every instant the value of voltage and current are different because it is sinusoidally varying, and we can represent using Vm sin omega t. So omega is a frequency and time t. See that the time. The V is a function of time, and here the V is also a function of the line segment. So that is coming to the end of this today's session. So you can refer to this model and you can copy to your notebook for further reference.